Good morning, students. It's, as they always say, for the first day of the week, I remember some of my colleagues back when we were on campus, they'd say a happy Monday. I think I started saying that, and then everyone started saying that. And then, of course, every day gets happy Tuesday, happy Wednesday, whatever. Uh, we all have challenges during the week. And I think I guess for most people, the most challenging day is sometimes Monday. It may be the last day of the week. I guess it varies for everyone. But I hope you're enjoying the more temperate climate. I know I am, and it's nice to be able uh, to be outside and it be, a reasonable temperature. Don't get me wrong, I like cold weather, but I don't like Arctic weather. I think we can do without that. I did send out the Blackboard message with the email about the next test. Basically, the same setup as the first test and the sections that are covered. And I was very pleased with this class for the most part. When you scan your work, that you make one file. There are lots of apps for phones that are free. Like I say, the one that I use is the Adobe Scan because I have an Adobe account. There actually have one with the school, but this is just a personal one. And but they all pretty much do the same thing as you basically photograph your papers. You just scan however many you have, and you can also, orient them so that they're right side up, and then you save the file. But whatever method you use, I'm grateful for that. I've had many students use varying methods. One student even did a Zoom video of his work for a pre-cal class that I teach, and it was fine because I could hold the video, pause it, and very clear picture, and that worked fine. So one file, some send a video file, some send a zip file, some send the PDF. uh, but in any case, I need to be able to scroll through your work, and it really does help when it's not upside down. The PDF allows me to move things around, but other formats do not. So that's really important when you make your file. Just check to make sure it's clean and everything's oriented well before you drop that into the Turnitin. So like I said, I'll do some review problems on Wednesday as I did for the last test, maybe cover a couple of other problems that I don't get to today in the new material, and then cover some review problems that'll help you with additional preparation for the test. Now, what we're going to do today, of course, none of this material will be on the test. I want to start with the partial fractions since I pretty much introduced that when I covered the lecture material on 8.1, and then back up to the trigonometric substitution. I think the order doesn't really matter, and I think since I've already pretty much introduced the partial fractions, I wanted to go ahead and just continue with that, and then, like I say, back up to the trigonometric substitution. So let me go ahead and share my screen. So back when we were recovering from our winter weather, I did a computation, and this one was just actually one that turns up a lot. The partial fraction decomposition for the linear factors is very easy. And so what we do is we think of taking a fraction and reversing the process. Normally, we get a common denominator and make one fraction. Now we start with the fraction and we decompose it. So I showed in that video that this particular integral had a very straightforward antiderivative using the linear partial fraction. So we got 1 over 2a, the natural log of the absolute value of a minus u divided by a plus u. And you should go back and look at that if you don't remember it. And in this particular case, this was where, of course, u is a differentiable function of x. So the idea here is that you can take this difference of squares, which gives you two distinct linear factors, and go backwards. Now, what other types of expressions would we need to deal with? Well, since we're dealing with real expressions in calculus, we could have irreducible quadratics. That is with the fundamental theorem of algebra. As long as we have real zeros, we can just map it out with linear factors, x minus the zero, et cetera, like you did in pre-cal and college algebra. But the other case is when we actually have what we call irreducible quadratics. So for instance, for irreducible quadratics, we use a linear numerator. That is, when you talk about the linear factors, you just have an a over the linear factor and a b, different coefficients. But we need linear in the sense that there could possibly be an x term. And this looks like this, ax plus b, etc., cx plus d. So the idea is that there's a possibility that in the numerator, we have an x term, or we might have a b term, or we might do both. It's inclusive. So we don't know that when we go backwards. And what I want to do, just like I did up here, is show you techniques to determine these coefficients, which are very straightforward. I think you're going to like this, and it's easier than the trig integrals. So here's an example. We have the integral of x squared plus 5. So we're taking these rational expressions and decomposing them. Now, of course, if the numerator degree is larger than the denominator, you'd want to divide first, just like you did in pre-cal and college algebra. That'd be like a calculus 1 integral, where you'd end up with a quotient and a remainder. And so now we always want to do that first. But of course, in this case, we have a numerator of degree 2 and a denominator of degree 3. So we don't have to do any division. Now, one thing that's interesting about this is that you can look at this and, we always do the easy check. We check 1 and minus 1. Clearly, if we substitute 1 for x, we don't get 0. But if we do the negative 1, we get 3 negatives here, which will make negative 3, and 3 to give us a 0. So checking 1 and negative 1 for possible zeros is always easy, and we do that first. So what we want to do is go ahead and factor the denominator. So we have a 0 of negative 1. We'll just use synthetic since it's easy. Of course, when synthetic is applicable, it's quick. So we bring the 1 down. 1 times negative 1 is negative 1, plus the negative 1 is negative 2. And then negative 2 times the negative 1 is a positive 2 plus 3. Okay, plus 1 is 3. And then 3 times the negative 1 is negative 3, plus the 3 is 0. So we do get the 0 that we know we should have just by observation. So this implies that we have x cubed minus x squared plus x plus 3 is now x plus 1, or x minus the negative 1 here, and then times the reduced polynomial, x squared, which we just read from the coefficients, minus 2x plus a 3. Now, this is what I was talking about before. If you look at the discriminant here, it's negative. So b squared minus 4ac is negative. So this, as I wrote up here, is an irreducible quadratic in R. It has imaginary zeros, but we're not working in the complex plane. So this is the irreducible quadratic. So when we do the decomposition, we have to make sure that our symbolic numerator has the linear form. So now what we can do, so we take this integrand and work on the coefficients for the decomposition. And once we have it, we go back to the integral, break it up as we have, and do those integrals. So basically, we're taking a rational function, maybe it could be in trig functions or x or whatever, and we're decomposing it to make simpler integrands. And usually we can just take care of the integrals with maybe some inverse trig forms or some calculus one forms. So we have x squared, and let me show you some of the techniques that will be very valuable for doing this. Students, think, oh, I have to set up linear systems of equations. No, you can use calculus and just some really straightforward techniques like we do um, with the integration by parts to make this very doable. No need to do extra work. Extra work is just no fun. If we have to do it, fine. So now we have our first linear factor. So that just gets an a over x plus 1. That's a distinct linear factor. So the decomposition would have this form, and we would need to determine the a. And then for the next factor, which is the irreducible quadratic, we need to have a linear numerator. So we'll just start with b, bx plus c. These could be the same, but we don't know that. So we have to give them different letters. So this will be x squared minus 2x plus a 3. So again, remember that we're okay using A, B, C, D. We're not going to run out of letters with these problems. A lot of text will use an A1, A2, A3, things like that, because that's an infinite list. But I'll just go ahead and use our regular alphabet because that's going to give us more than enough letters to use here. Now, what we want to do at this point is just to clear denominators. So we're going to multiply through by this denominator, considering this factored form. So we want an equation that will be true for all real numbers. So this will be x squared plus 5 equals a times, just go ahead and copy over here, x squared minus 2x plus a 3 plus, now we have bx plus c times the x plus 1. So now when we multiply both sides of the equation by this, we see that the x plus 1 absorbs and leaves us with the quadratic. And here the quadratic absorbs and leaves us with the linear. And then, of course, over here, we just have the numerator x squared plus 5. Now, to find the coefficients, we use very straightforward techniques. So the first thing we notice with the linear factors, this is true for all real numbers. So we can just let x equal -1 to figure out what a is. So we'll start out simply and say x equals -1. Okay, so now we say if x is -1, this will give us a -1 squared plus a 5. So this will be a 1 plus a 5, which is a 6. And then, of course, here we have the a. And then we have what, -1 squared minus 2 times the -1 plus a 3. And the beauty of this is that when you substitute the -1 here, this is obliterated, this is annihilated. So we just have, if you like, just the plus 0. That's the whole idea of choosing the -1 here. This works for all real numbers, so we just use a convenient number to annihilate this term. And so now we see that we get an a, and we have a 1 and a 2 and a 3. So 1 plus 2 plus 3, which gives us a 6a. So now when we compare, 6a equals 6, so the a's absorb, and this gives us an a equals 1. Okay, so now we can take our equation here and go ahead and fill it in with the a just to make our work easier. No need to do too much work. So this implies that now we have x squared plus 5, and now the a is just a 1, so this gives us x squared minus 2x plus a 3. And then, if you will, just to make our work a little bit easier, I'm going to show you a very interesting technique. Go ahead and multiply this out. This will be in bx squared plus a bx, and then plus a cx plus a c. Now notice, it's like, okay, we're in a college algebra class or algebra 2 class, and we notice here that the x squares just absorb. So we might as well just remove those. They're just in the way. And then, of course, if you like, we can take the 2x over and the -3, and this will give us a 2x plus a 2 equals bx squared plus bx plus cx plus c. Now you're thinking, why am I doing this? Well, now I'm going to show you a technique that you don't often see in textbooks. It's just because at this point we've done very simple algebra. And all we need to do now is figure out the b and the c. And you can say, well, we could substitute numbers, but that's too much work right now. This is a differentiable equation. So let's differentiate to kill off some of the coefficients and then solve and then back substitute. So here's what I'll say. Differentiate, D-I-F-F. So we'll get 2 plus a 0. Then we get a 2bx plus a b. Remember, b and c are constants, plus a c. And we've annihilated that c there. And then we're thinking, this is good. Let's go one more time. Let's differentiate again. Differentiable equation. We get a 0. And of course, here we get a 2b. And these are both constants, so we get a 0. So 2b equals 0, if and only if b equals 0. So this differentiation technique is just as useful as substituting a convenient value of x. And most students look at these problems and they just say, oh, there's so much work. No, this is easy. This is simple work. And the idea is that we just have to remember what it is we can do in calculus. Oftentimes, students will get to a point in a problem and just stop. And it's like, well, do some calculus, take a derivative, take a limit, do something you know how to do, because all of these techniques are at your disposal. It doesn't mean you have to ask permission, just do it. And so now if we see that b is 0, we can go back to this equation and just substitute b equals 0. So we have 2. So these together imply 2 equals, well, we get a 0, 0, and a c. Well, c is 2. So from the standpoint of using convenient numbers, we reduce the equation to one with 2 unknowns. So in order to eliminate an unknown, we differentiate, determine one of them, and then back up and get the remaining one. So now we see that our decomposition is very easy. So now we can go ahead and complete the problem. And so I have a little extra room. I'll just go ahead and continue this on a new sheet and move this up. So we've got our coefficients. And so now we have our problem. That is, let's go back to the original problem since you've probably forgotten it. So this is what we started with. And now we can fill everything in. We have a, I'll just move this down. We have a, which is what? 1. So this gives us the integral. I'll just put the 1 there for effect, 1 dx over x plus 1, real simple integral there. And then plus, well, notice here, we have the b is 0 and the c is 2. So we get 2. And then, of course, we have x squared minus 2x plus 3. So let's just kind of summarize. We look at the decomposition, and then we use elementary techniques to determine a, b, and c by substitution of convenient values of x in this equation, or by differentiation and just back substitution. Very simple techniques. And now we notice that we have reduced our original equation to two very doable integrals. This is just du over u, but of course here we're going to need to complete the square, and hopefully we'll get one of the inverse trig forms that we can deal with. So let's go ahead and work through that. So this gives us, I'll go ahead and write this again, dx, and we'll compute it, x plus 1. And now we can complete the square here. If you like, you can just leave, and of course we need a dx. Dx is always hanging out, even if Professor Ron leaves it out. You always have to check. I mean, before you hit that enter on WebAssign, double, triple, quadruple, you know, what you meant to write and what you should write are often two different things. So again, that's why you write everything down and double, triple, quadruple check. That's what a STEM professional has to do, unfortunately, but it's a good thing because it's making you better at what you do. So now this is monic, so we'll take half of this. So x squared minus 2x, half of negative 2 is negative 1, square it. So we get plus 1 minus 1 plus a 3. So there's our perfect square. So now we get natural log of x plus 1. And then we get plus, in this case, we have a 2 dx. And then we have our perfect square, x minus 1 quantity squared plus a 2. So now this is just the inverse tangent form. So if you look at this, we have u equals x minus 1. And of course, a is the square root of 2. We write 2 as a perfect square. And of course, du equals dx. So we don't have to, no work is done here. The 2 is just hanging out. So we're stuck with it. So now this gives us natural log x plus 1 plus, and now remember we do 1 over 2a. So we have 1 over a. So we have 2, which is already there, divided by the square root of 2. That's the a. And we have inverse tangent of u x minus 1 divided by a. And then, of course, we can tack on the c. And if you will, we can just absorb the root 2 into the 2. Certainly not required, but, you know, sometimes we take the time to make things look a little nicer. But, you know, if you don't have the time, it's fine. You just have to figure out, if you're on the test, pick the expression that's equivalent to it. That's why we always work out our algebra to make sure that we're getting expressions that are clean and at least gives us the ability to check equivalency with other things. So what we can see here is the process of decomposition is a very algebraic one, which you could have learned basically in Algebra 2 or college algebra. The process is simple. If you have linear factors, then you have the constant numerator. If you have the irreducible quadratics, then you have the linear. And then, of course, if you have repeated factors, you just have the x plus 1 squared and then another constant, call it a b if you want. You don't know what these constants could be, what these actual coefficients are going to be. And so you can't assume anything. So you have to at first set out that they're all different. They could very well be the same in many cases. So, you know, you start with A and just use as many letters as you need. Okay. So just remember the irreducibles require the linear numerator, the linear ones, just the constant numerator. So that's the key here. Very simple, just like when we derive this. The idea is that the distinct linear factors present the easiest case, whereas of course with the irreducible quadratics, we can use convenient values of x, which we always use regardless of the type of factor here, and then the concept or structure of differentiation to decrease the degree and also to eradicate certain constants. So it's a very easy technique and something that you don't normally think about. So take full advantage of it. It's so simple here and so easy to do and so easy to check your work. Okay, let's try another one. Now, when we think about what we're doing with this type of work, let's see here. I've got another example here. Let's see where did I put that one. Oh, here we go. Yeah, let's do this one. And then we'll move over to the trick sub. I like this one because it's a definite interval. You know, Professor Ryan likes the definite intervals, but they give us good practice. So let's look at this one. And then we'll do some right triangles, which again won't be difficult and be very useful. So we've got in this case the integral of 1 to 2 x plus 1, a little bit simpler to I want to say analyze because we don't have to use synthetic division. And it comes to us in a very nice form. So in this particular case, we have a very similar situation. I always like to do the ones with the irreducible quadratics. For the distinct linear factors, you don't need me. I mean, you don't need me. I mean, that's simple. So I try to focus on the techniques that will help you build your understanding. So now when we look at this, we have a definite integral and we have a linear factor here and we have an irreducible quadratic, plus or minus I, of course, if we were in a college algebra class. So now what this is going to mean first is that we need to do a decomposition to produce expressions that we can now what? Differentiate, excuse me, integrate, because in this form, we are hard pressed to figure out an antiderivative. So we're seeing now that the antiderivatives don't look anything like the integrands anymore because the technique's more complicated. And we noticed that, I think most, when we started doing the integration by parts, it's like, there's no way to go backwards unless you just pound it out and differentiate and verify. So here we have A divided by X. Again, we have the distinct linear factor. And then, of course, we have the irreducible quadratic. So we can use the same letters if you like, bx plus c, x squared plus 1. So the idea is that you basically use your common sense to set this up and don't worry, you know, I mean, if you just have an x squared, then we'd have a b over x squared term, and then we'd have to use a cx and a d here. So the repeated linears and just like repeated quadratics, just add extra terms with different coefficients, but just the squared part. So basically what we want to do, ladies and gentlemen, is have a term that corresponds to each of these factors, okay? And then we can do the backwards process. So at this point, just like we did before, let's just go ahead and clear denominators. So multiply through by x times x squared plus 1. So we get x plus 1 equals a times x squared plus 1, the x is absorbed, plus bx plus c times an x. So this is not as busy as the last one, but it does present some good practice with the definite integral. So again, when we look at this, we're thinking, okay, well, you know, we can always choose x equal to 0 because that will annihilate this term. The linear factors are simple, and then we can solve for a. So let's just, you know, be straightforward with this and say x equals 0. And so now when we substitute 0 for x, we just get a 0 plus 1, which is 1. And then this equals a times 0 squared plus 1. And then, of course, this term is annihilated. So we just get a times 1. So in this case, a just is equal to 1. So it's so simple. Sometimes you have to do a double take and think, well, can it be this easy? Absolutely, absolutely. It's just a little bit more mature, you know. Maybe this wouldn't go over as well in algebra 2 and college algebra because maybe you wouldn't have anywhere to use it and then you'd forget it. But, you know, with with every class, sometimes I'll introduce things early just to say, okay, we got some extra time. What about this? What does this mean to you, or is this something you can understand today? So now, when we look at this, we're thinking, well, let's just go back to the equation and see what we have. So equivalently, if we replace a with 1, we get x plus 1 equals x squared plus 1. Again, a is 1. And then we can multiply this. We'll get a bx squared plus a cx. And now, of course, we can't really absorb anything. We can absorb the 1 here. Yeah, well, let's just go ahead and get rid of that. The 1's gone. So we get x equals x squared plus bx squared plus cx. So that's our new equation. Now, one thing that's interesting about this, if you compare it to the last one, we've got the same situation. So let's differentiate to get rid of the c. So let's do that. Let's just go ahead and move the calculation over here, and Professor Ron can use the space on the page. So we'll differentiate. So we get 1 equals 2x plus 2bx plus a c. Okay, so we're still kind of stuck with two coefficients here. So let's differentiate again. Again, these are differentiable equations. So we get a 0 equals 2 plus 2b. And of course, the derivative there is c. C is a constant. So now if and only if you want to just run everything over or just factor this, you can just say -2 equals 2b, and the 2's absorbed, so b must be -1. So when you look again at this, very similar to the last one, and so now you can say, okay, well, if we've got b equals -1, we can go back to this equation, and this implies that we have 1, and this, now what we can do, and like I say, it's interesting when you think about this. If we've got this, we can say, well, let's substitute b equals -1 and then pick a simple value for x to solve for c. So let's do a 2 for here. So first, we're going to say 1 equals 2x, that's from this equation here, plus 2 times the -1 x plus a c. So equivalently, this gives us 1 equals 2x. Well, everything's falling out. 2x. Well, I didn't have to worry about it. I was thinking, well, we'll just do step 2. These absorb. So, of course, c equals 1 because this just gives us a 0. How funny. I was thinking we're going to get to substitute a number, but we don't have to. So when you go back to the equation and substitute the value for b, then you can look at this and say, okay, well, if that's the case, then if I need to, I can substitute a value for x of our choosing to be able to work the problem forward, but we don't have to. So we've got all of our coefficients. So now what does this imply? So we've got our original equation here, and we've got our decomposition. Now we can fill in all the constants here, the coefficients a, b, and c. So we have the integral 1 to 2 of x plus 1 divided by x times x squared plus 1 dx. So let's just run over here. A is 1, so we get equals 1 to 2. So we have, in this case, I'll just write 1 dx just for emphasis, even though that's a little bit wasteful, but that is, we have a 1 here, so 1 dx. So apply the integral to this, plus 1 to 2. So we have a -1, so we have a negative x plus 1 divided by x squared plus 1 dx. So now when you look at this particular problem here, this is going back to the beginning of the class where we just have to break this up. You can see now we don't have to do anything fancy here, no fancy algebra, because this part right here will just give us a calculus 1 integral, and then this part over here just a inverse tangent like we had in the last problem. So it really just depends on how complicated this is as to how much work you're going to have to do. Since we can go ahead and fix this really nicely with the 2x, we don't have to do any fancy algebra. So that's actually pretty simple. So now let's go ahead and write this down. We know this is the natural log of the absolute value of x. So we have natural log of the absolute value of x, 1 to 2, plus, so we have 1 to 2, we have the negative x, x squared plus 1 dx, plus 1 to 2 dx over x squared plus 1. So that's pretty simple. Now, if we look here, we can just go ahead and keep the same variable, but we have a u equals x squared plus 1. So du equals 2x dx. So all we need is a 2 here, and we can just pay for it, and we can just take the negative outside if you like. So this will be the natural log. We'll just go ahead and do the fundamental theorem of calculus. So we have natural log of 2 minus natural log of 1, those of course being absolute value. Now we'll have plus, and then we'll just do the negative 1/2, the negative there. So to pay for that, factor the negative and pay for the 2 with a 1/2. 1 to 2. So this will be a 2x dx, as we have here, divided by x squared plus 1. Now we can go ahead and move this one forward. Notice the a is 1 and the u, or omega, is just x, so that's simple. So this will give us an inverse tangent. So in this case, we'll just say omega equals x and a equals 1, d omega equals dx. So that one's good to go. So we have inverse tangent 1 over a, and then this will just give us what? X squared plus 1. Oh, sorry. Ding. X. And then we'll evaluate from 1 to 2. When it's so simple, we want to put in more. So now we just have the standard arctangent form for the antiderivative here. And so we just get, in this case, omega over a, which is x over 1, 1 over a, just a 1 there. So that's so simple. And then, of course, here we're ready to do this because this is table ready. Of course, the natural log of 1 is 0. So we get log 2, which we can just write that way. And now this is du over u. So we get minus 1/2 the natural log of the absolute value of x squared plus 1. But that's always positive. So we can just write that as x squared plus 1, evaluated from 1 to 2. Then we have plus, we use the fundamental theorem of calculus here, inverse tangent of 2 minus inverse tangent of 1. And of course, we know that's pi over 4, but we don't have a nice value for that. So now this gives us ln 2 minus 1/2. And so when we substitute the 2, we get a 4 plus 1. So that's a log of 5. And then, of course, when we substitute the 1, we get a 1 squared plus 1. So that's minus a log of 2. And then, of course, we get plus inverse tangent of 2, and then minus a pi over 4. Now, if you like, and this is your choice with this problem, there, if you like, notice when we distribute the minus here, we're going to get 3 copies. Well, basically we've got a half copy here and we've got a one copy here. So we can do a little trickery. Let me show you what I'm talking about. We don't have to do, this is okay, but a little bit messy. So this is ln2 minus 1/2 ln5. And then of course we have minus minus. So this is plus what? 1/2 ln2. And then of course we have the plus inverse tangent of 2 minus pi over 4. This is still kind of messy, but notice we can put these two together and this gives us 3/2 natural log of 2. Now, and of course we have the minus, you're seeing what I'm doing here. We're going to go ahead and eventually put these together. So this term we just write down inverse tangent of 2 minus pi over 4. And of course, if you got to this point, Weber sign would be fine, but you might be looking for a response that's a little bit cleaner. So we can use our laws of logarithms. So now notice we have the 1/2 here, which is fine as a coefficient if we wanted to use the quotient rule. And so we're just going to move the 3 by the power rule up here as a power of the argument 2. So this will give us, excuse me, 1/2 log of 2 to the third minus 1/2 ln of 5 plus inverse tangent of 2 minus pi over 4. And now, of course, that's just an 8. So we can do the 8 and the 5 as the quotient rule. So this will give us 1/2 natural log 8 over 5 plus inverse tangent of 2 minus pi over 4. So that would just be a way of making it look very nice. So when we get to this point, we're just collecting terms. And we know we can use the quotient rule and the product rule as long as the coefficients are the same. We can always pull out that coefficient and then combine the terms with the sum to make the product, or we can combine the terms with the difference to make the quotient. So this here is actually much more tidy. So like I said before, the definite integrals certainly introduce some additional arithmetic. And then of course, if you want to make your solution look a little more tidy, you can. But of course, if you're doing your WebAssign and you want to stop here, that's fine. That this is completely equivalent. But it's always good to practice to make it in just a more tidy form if we can do it. So that's just part of being a good math student. But not required. When I say not required, if you don't have to do it, fine. But if you're looking for an equivalent expression, then you might have to do a little bit of operation on it to make sure. I've had students before when I'd say, give me the exact number for a radioactive decay problem. So they're sitting there, well, let me check to see what this one is. Is that one right? Oh, I finally got it. And I look at their work and it was really good. They didn't want to spend the time to do the algebra. So they just punched buttons on their calculator, which I didn't particularly like, but it certainly was a good technique. It worked. So I had to, hats off to them for using at least good problem solving techniques. So what we can see here is that when we're doing the partial fraction decomposition, we are adhering to the same set of rules. The best way to do this is to practice. You can write the rules down all day long, but it's not going to get you where you want to go until you actually see the method. And what I really wanted to point out today is that you can, once you have your equation, you can substitute any value for x as a means to solve for a particular coefficient. You can differentiate to remove coefficients to solve for one and then back substitute. So that gives you a very, very powerful technique to solve for these coefficients. You don't have to, make a system of equations, which would take you forever. this technique is easy to execute and something that I've developed all kinds of interesting techniques, and I really have to have my hat off to Oliver Heaviside because his techniques are just amazing at what they do, and they illuminate what's going on in a way that you can check your work, and you can always go back and easily check this work. If you, the derivatives are so simple, but if you have a slip up, you can always go back and check. So that's a nice attribute about this technique. Okay, so very good. Now, what I want to do is talk about some right triangles, which you know quite a bit about. That is, this is called trig sub. So short for trigonometric substitution. Now we've done trig integrals and you saw all these. Remember these? Remember these? You should have these on a note card. The reduction formulas. They are very handy. You can always use your power reducing when it's simple, but you got a single trig function to a power, very handy. And a lot easier to execute than making 500 algebraic mistakes unnecessarily. So for trig sub, what we want to do is just look at the fact that right triangles with Pythagorean radicals are very useful to us. For instance, we can think about doing problems that otherwise might be very difficult if we think about a right triangle that we pretty much learned about in pre-calculus. So here's an example. The first one we want to do is this integral. I want to lead by example here. You can beat this to death again with basic equations, and I'm going to go back to some special formulas that we can use. But we often saw that when we were doing arc length in chapter 7, that for problems that seemed like, well, why don't we do the length of a quadratic? You know, like y equals x squared. I mean, what's so bad about that? Well, the problem is that when you do the arc length radical, you get an integrand that we don't know anything about, at least in terms of finding an antiderivative. We don't have a circle. We end up with an arc of a hyperbola. And then that's a much more complicated geometric task. So the thing is that now we'll be able to go back to that problem and make some sense out of it. Whereas many times we might think that curve length is very trivial, but it's not. I mean, we had those very strange functions that worked out to nice perfect squares that we could actually move forward, but look how much algebra we had to do. So now we're going to say, okay, there's less algebra, but we have a harder integral. So when you look at something like this, you're thinking, okay, we haven't encountered this before. That is, if you look at this particular expression here, this is Pythagorean, and I've got 3 copies of it. So the first thing that we would want to do is to break it down a little bit. Is we can write this as the square root of x squared plus 3 to the 3rd power dx. So when you look at that, you're thinking, oh, okay, this is a right triangle. That corresponds to a right triangle. Let's draw it. And then we can make some more general observations. So we couldn't do this before with the standard inverse trig formulas because this doesn't fit any of them. It's not inverse sine because we've got a plus. So just remember, if you run into an inverse trig problem, don't do the trig sub, you don't have to. But if there's extra stuff hanging out and you can't rig it, then you may have to do this process. So notice here, we can easily draw a triangle. So we've got basically a u squared plus an a squared. So we're thinking if we have a theta here, we can easily write the radical here as the hypotenuse of a right triangle because it's a sum. So we could say x divided by the square root, well, excuse me, x for the opposite side, and for the adjacent side, square root of 3 for theta. And then, of course, here, the hypotenuse is just x squared plus 3. So this is just working backwards from the radical. The Pythagorean radicals correspond to a right triangle. And so now you're thinking, oh, okay, look here. We can replace the radical with a trig function. That is, if we make a substitution for x. So now when we look at this triangle, we see tangent of theta is x over root 3. So this implies tangent of theta equals x divided by root 3. So if you think about it this way, you can actually work your problems this way and never screw them up. I mean, you always be like, I know this is right because there's my right triangle and it fits that radical. So now if and only if, watch this, x is just the square root of 3 times tangent theta. So what we're seeing here is that when we have a form u squared plus a squared, we can use this type of substitution. So in general, we're thinking if we have a radical that looks like this, u squared plus a squared, what we want to do is let u equal a times tangent theta and use the inverse trig functions. So the key here is that with the inverse trig functions, this will work because we can always solve for theta. So basically what we want to do is take this integral and transform it by basically miscellaneous substitution, which you have here, into a theta integral, and then work it out. So this is really a form of miscellaneous substitution. So now if we look at this, we're thinking, okay, well, dx, we can do the differential. Dx equals square root of 3, and the derivative of tangent is secant squared, theta d theta. So this is just like the miscellaneous. So boom, we've got that piece right there. So just like when we do miscellaneous, we've just got a lot of pieces that we have to transform, okay? And now, so the dx is taken care of. The -3 is what it is. That doesn't change in any variable. And then, of course, now we can get the radical from this. So also, the radical x squared plus 3. So we've got, when we square this, we're just going to get a tangent squared plus 1. So we get the square root of 3 times tangent squared plus 1. Now, you don't have to do this every time. I'm just kind of writing it out because this way you can develop a formula. But now, of course, tangent squared plus 1 is secant squared. So we get the square root of 3 times the square root of secant squared. But remember, with the inverse tangent, theta lives here, negative pi over 2 to pi over 2. And for these values of theta, the secant is non-negative. That it corresponds to the cosine. So this is, in this case, square root 3, absolute value of secant, which now can be dismissed because of where the theta lives. So this is the square root of 3 secant theta. So when we think about the concept here, you're thinking, oh, okay, if we see this, boom, triangle. So some students want to just hang on to this, but then they want to look at that and say, well, that's just a hypotenuse. I can rig it, use tangent. And then if I write tangent, I know what x is. It's just square root of 3 times tangent theta. Then I can do my differential and then replace the radical with a trig function. So what the trig substitution does, ladies and gentlemen, is that it takes a integrand with a Pythagorean radical, or maybe the square of it. Here we've got the cube of it. Wow. And then replacing it with a trig integral. So this is why we needed to do the trig integral first, because this is what's going to happen when we do the transformation or the substitution. So now let's substitute everything. So now the integral, we've got all of our pieces here. So we have the integral, -3. And now the radical is square root of 3 secant. So we'll have square root 3 secant theta cubed. And then the dx is right here, square root 3 secant squared theta d theta. So this is just like miscellaneous, complete transformation. And students find this to be kind of halfway between integration by parts and trig integrals. Students don't tend to like the trig integrals just because it's like, you know, they always want to go an easy route, but the setup here seems to be very straightforward, basically because it's just the right triangle. And using the inverse trig, which we've kind of beaten to death, you actually know what those are now. So now we can say, we can see that a lot of things absorb. So let's see what we get. So we get a -3. Let's go ahead and pull this over root 3. And then, of course, when we cube the root 3, we just get 3 times root 3. So that's nice. 3 halves gives us a 1 1/2 right there, secant cubed. And then, of course, we're left with the secant squared theta d theta. Now, not all the integrals are going to turn out so simple, but there will certainly be integrals that you can do. And so now notice the 3 root 3's absorb. We're left with the negative. So we have a negative d theta. So these absorb. And then, of course, the 2 copies of the secant absorb, leaving us 1 copy of the secant. So we're thinking, well, that's nice. But of course, the reciprocal of secant is cosine. So we get the negative of the integral of cosine theta d theta. So if we look at what we're doing here, we have reduced this integral to this trig integral right here. Now, how complicated the trig integral is will just be a function of how complicated this is or whatever it is we have to do. But so we're seeing that when we have this Pythagorean radical with the u squared plus the a squared, we see that this substitution will transform this into hopefully what we find to be a simpler integral. So the transformation process depends on the type of Pythagorean radical. Now, of course, when you don't have Pythagorean radicals, you can get functions that require the elliptical integral setup, which is a more advanced topic. I've done that before in honors classes, but they said, pass. No, it's one of those things as engineers and future engineers you will see, and your professor will say, well, here's a nice table for these, so don't sweat it, kind of thing. But as long as we can see that we have the Pythagorean radical, we can use this trig sub. Of course, we always are grateful when we have an integral that's doable. And of course, as you do more mathematics in your at the university, you will learn some new techniques that will take care of certain mathematics that arise in particular engineering problems or computer science problems or physics problems. That's just kind of the nature of what you do. So you pull in the math that you're going to need to solve particular problems. So now when we look at this, the antiderivative, excuse me, of cosine is just the positive sign made negative. So this is the negative sine theta plus a constant. Now you're thinking, are we done? Well, we're just like, we didn't do a definite integral, so we didn't get a number. So this is why it's very convenient to have the triangle that represents the Pythagorean radical. So now we can just do sine of theta, which is opposite over hypotenuse. So this will give us negative x divided by the square root of x squared plus 3 plus a constant. So what you can see here is that it's not always the easiest thing to figure out, well, what do I do with this? How how do I solve this problem? It doesn't look like anything we've done before. I've had many students come back and say, Professor Ron, I can't do this integral. It's too difficult. And I said, that's just a basic trig sub. And it was so simple. It's kind of like doing, dx over x squared plus 1, inverse tangent of what? X. I mean, you want to slip up and make it harder than it is because there's not much there. So now what we can do is that when we have the Pythagorean radicals, we can actually use the right triangle to do a miscellaneous substitution. So basically, this is a complete transformation. This is not the standard table ready, excuse me, rig the differential and we're good to go, add 1, divide by the new power. This is a complete transformation. And you can see it's very algebraic. So just like the partial fractions, you have more steps, but the steps are fairly straightforward, okay? Now let's look at another example, maybe that has a definite integral, so we can try another one of the substitutions. So here's one of our substitutions that we need to know. Let's look at another one, and we'll use an example to kind of motivate it. So here's another example. We have the integral uh, 0 to the square root of 3. So it's thinking unit circle, right? Square root of 3 over 2. We have t squared. And here we have 1 minus t squared to the 3/2. Now, I'm not trying to be a broken record, but I think it's good when you have the Pythagorean radical to different powers. It makes it a little bit more challenging and keeps you on your toes. So just like the previous problem, I thought this would be a nice example now to take a similar technique with a different substitution, but now with a definite integral, which again, we're thinking, do we change the limits? Well, absolutely. Sometimes in the WebAssign problems, they say, well, don't change the limits, go back to the original variable and do it. Well, you don't have to do it twice. That's ridiculous. You're not going to do it twice, because if you've got a situation like this with the trig sub and a definite integral, you want to change the limits because it's just ridiculous to go back to the original variable. That's doing twice the work. So when you get to those problems, just type the same answer. If you get your little green check, just type the same answer. No need to rework it. I think what the author's trying to do is like, well, if you did it this way, like your professor does it, he doesn't change the limit, or excuse me, the variable when it's very straightforward. So in this case, I would always advocate changing the limit because it's going to make the process easier and quicker. Now, when we look at this, we're thinking, okay, well, let me go ahead and put this in a more user-friendly form, just like we did the last one. So we have 0 square root 3 over 2. We have t squared dt. And then we have the square root of 1 minus t squared. 1 minus t squared cubed. So now you look at this and say, oh, okay, that's a right triangle. I wish I didn't have the limits because that's going to be extra work, but that's a right triangle. So let me draw the triangle, and then we can say, oh, well, this is another Pythagorean radical, and we can have a substitution like we had for the tangent. So now we're thinking, all right, let's just draw a triangle. We can use theta. You can use beta or alpha, doesn't matter. So we have a theta here. And then you're thinking, in this particular case, there's the hypotenuse right there, because now you're subtracting a leg. So here you've got what? Opposite. So you've got t. Put your 1 here. And then 1 squared minus t squared, square root, gives you the adjacent side. Now, of course, these are not unique, what I'm setting up. I mean, you could use whatever trig function you wanted. One time I said, well, let's just make up one. And I told students, I said, this is fine and this is fun, but let's stick with the standard because you have enough to remember. So the idea here is that you're thinking, okay, how can I get this out of this particular problem? It's like, how can I make a nice substitution for t? Well, look, sine of theta is just t over 1. So you're thinking, oh, okay, so I'm going to replace the t with the sine, and then I'm going to have the 1 minus the sine squared, and that's going to give me the cosine squared, just like we had before with the secant squared. So now you can see this implies, and of course it's so simple, sine of theta is opposite over hypotenuse. That's just t. So when you look at a problem like this, it's like, well, there's no coefficient here, so I already have t for free. Boom, right there. So now when we think about this problem, we're thinking, okay, in general, if we have a squared minus u squared, like we have here, a squared minus u squared, let's just use u equal a sine theta for the substitution. And that's a standard substitution that will always take care of a radical of that form. So again, a standard form. Of course, you could vary it or whatever, but no need to. Stick to the convention because it's nice and simple. Now, of course, this rectangle will kind of be the triangle will be kind of the governing body, so to speak. It's like this is basically giving us the trigonometry of this particular substitution. So now we're thinking, let's just go like we did for the last one. And then, of course, we'll change the limits. So we have dt, and the derivative of sine is cosine. So we have cosine theta d theta. So boom, we have that right there. Now, what we can also do is, okay, we need a replacement for the radical like we did before. Let's go ahead and compute that. So now 1 minus t squared, that's just going to give us 1 minus sine squared. Now, of course, when we think about this, sine, or the theta, by the definition of the inverse sine, will live between negative pi over 2 and pi over 2, just almost like the inverse tangent, except we include the endpoints. And so now we get the square root of cosine squared. And of course, you don't have to spend so much time on this. You can kind of write down formulas for these too, if you like, or you can just do the computation. So this will be the absolute value of cosine. But by restriction on theta, the cosine here is non-negative. Excuse me, so we get cosine theta. I tell you, you know, I'm so excited about the nice weather, and I get up and I run and I do my cycling, and it's amazing the weather we have in Texas. It's like my sister in Montana, you know, they go snowshoeing because there's 10 feet of snow on the ground, okay, which is great exercise, but there's so little oxygen in the air. It's like you go 2 feet and you feel like you run a marathon. So I like our Houston weather. I think I've gotten used to it. So now when we look at this, we're thinking, all right, well, we can now go and do a substitution. And then we're thinking, oh, okay, we're going to get an integral that we did last week with integration by parts. You know, so I think, well, close to it, but we're going to get a nice trig integral. Let me say it that way. So now let's first go ahead and see what our new variables or limits are going to be. So now we want to go from t to theta. So if we look here, notice if and only if theta equals inverse sine of t. So let's do theta of square root 3 over 2. So that will be inverse sine of square root 3 over 2. And we think about the unit circle, that's pi over 3. And then we can do theta of 0, which is inverse sine of 0, which is 0. So when you look at these and when you think about these, unit circle, and now we've got our new limits, so we can do a complete transformation. So this equals 0 to pi over 3. And now, of course, we've got the t squared. So t squared will be sine squared theta. And dt we have right here times cosine theta d theta. And now downstairs, we've got the radical, which is cosine theta cubed. So we get cosine cubed theta. So again, complete transformation, and actually very simple. This is easier than partial fractions. But if you don't like trig, maybe it's a little bit harder. But it's very straightforward trigonometry, not the kind like we did last week where we're doing reference angles to the nth degree to figure out things. I mean, it just really just depends on how much time you spend on trig. And you got your unit circle out, you can always use that as a reference. So now notice one of the cosines will absorb, and we get 0 pi over 3 sine squared over cosine squared. And of course, this is just tangent squared. And we don't need the the reduction formula because that's just Pythagorean identity. That's fairly straightforward. So we end up with an integral that's, pretty simple. So for tangent squared, we just, again, you can use the reduction formula, but that's a little bit overkill. So we'll just go ahead and replace this with secant squared minus 1 using the standard Pythagorean identity. So we get 0 pi over 3 secant squared theta minus 1. So now look at this, ladies and gentlemen. This integral is now transformed into this integral. I mean, once we do this and we clean it up, we see that these are equivalent. This is doable. In this form, it's not. So we do the transformation with the trig substitution to create a trig integral that for the most part will be doable. So again, think of this like calculus 1 when we had miscellaneous substitution, because this is a complete transformation. This is one, when you think about miscellaneous and integration by parts, you think of those techniques as being some of the most powerful with the antiderivative. And once you master those, you can always move into other types of integration processes and never, ever lose your way because you've got the foundation with these. So now, of course, the derivative of tangent is secant squared, so we're happy for that. So that's tangent theta. We'll go ahead and just say 0 to pi over 3. And then, of course, this is just a theta minus theta. I just broke this up into 2 pieces just to do it differently. You don't have to. You can just leave it alone. Doesn't matter. So now we get what? Tangent of pi over 3 minus tangent of 0. And then we have minus, so we've got theta. So we have pi over 3 minus 0. So now when you look at this, we're going to get the tangent of pi over 3. That's just square root of 3. Remember, sine over cosine. The 2's drop out. And then, of course, the tangent of 0 is 0. And then we have minus pi over 3. So what you're seeing here is that when we see the Pythagorean radicals, basically, we jump right to the triangle. So you don't have to maybe play as much detective work. You can just say, okay, if I have an a squared minus u squared in a radical or some power of it, squared, third power, whatever, or some power of it, I can use this transformation. And there's one more that's also standard. And these 3 standard substitutions take care of all these cases, as long as you have a Pythagorean radical or a power of it. Like I say, if it varies from that, these don't necessarily work, and you have to use other techniques, which again will come in future courses. Now, what I want to do is to showcase the next type of substitution, which will be the secant substitution. So this one, this one's like the logarithms and all that, you know, just never seem to run away from us. You know, we think we're done and then we want to make the problem look nice, and that takes more time than the problem. So here we go. Let's try one where we look at the last type of substitution. Again, this is a definite integral. This is a standard one. I like this problem, and it works nicely as an example of the final type of trig substitution that we'll study. So we get x squared, and then we have the square root of x squared minus 9 dx. So now when you look at this, you're thinking, okay, this is not quite what we had before. Before, we either had the u squared plus the a squared, or we had the a squared minus the u squared. Now we have the u squared minus the a squared. Okay, that is different. So this would be the last possible case of a Pythagorean radical. And so we're thinking, how do we do this so we just like, you know what we're doing? So let's again, we don't have a power of it. So let's think about a rectangle. Well, not a rectangle, a triangle. Don't we wish it were a rectangle? It'd be so much easier, but wouldn't be much trigonometry, right? So now we're going to think of this in terms of secant. So now what we can see here, we see that we have a hypotenuse of, in this case, of x and a leg of 3. So we can go ahead and set this up for secant right there. Again, this is not the only type of trig function that would work. It's just that this has become the standard substitution. So, you know, and it's like, not all of them are as wonderful. This one, of course, gives us the issue with the domain where we get the plus and minus. So we have to be a little bit more careful, but we're used to dealing with that with the secant function. So now when we have this particular leg, this would be the x squared minus the 3 squared square root. So we get the radical for this leg. So now what we can see is that the secant of theta will be hypotenuse over adjacent. So we will say, in this case, secant theta equals hypotenuse over adjacent. So equivalently, we have x is equal to 3 secant theta. So, ladies and gentlemen, and we're going to get to use our secant cubed radical or antiderivative that we've already derived. So what we can see here is that this is the last example, so to speak. So we can say, okay, if you've got u squared minus a squared and you want to get rid of this radical, conveniently use u equals a secant theta. And this will give you simple algebra in terms of trigonometry. So this is the last type of trig substitution. And again, you can do this in a more abstract setting, but it's really not worth it, because the idea is that once you see how this works, then these formulas make sense. Of course, we could draw all the triangles in terms of u and a and basically do the same thing. But now I thought this morning, you know, when I thought about this, or actually yesterday, I said, I think I'm just going to take the example and then move it into the actual formula and see how that works, making it a little bit more realizable for my students. Again, how you think about something, it varies for every student. Some of you will say, well, I'm just going to remember this. That's easy to remember. That makes sense. Or I'm going to think of it this way. You can think of the shortcut method for the integration by parts, the tabular method, how we've done it, the algebraic process. There's always some process that makes sense to you because it suits the way you think about math. And of course, that's a very personal thing. So that, you know, put your own signature on these to make them realizable. So now when we look at this, we're thinking, okay, how can we finish this off? Well, first, let's just go ahead and look at what theta is. Theta, if we divide by 3 and take inverse secant, we get inverse secant of x over 3. So we can go ahead and look at the new limits. So just like the last one, we don't really want to worry about not changing the limits and do the integral without the limits and then go back. Not the best way to go for it. Just go ahead and change the limits. That makes it a little bit easier. And so now we can say theta of 6 will be inverse sine or inverse secant of what? 6 over 3. And that's something we know. This is inverse secant of 2. That's basically where we have cosine of 1/2. And what is that? That's pi over 3. So that's just unit circle. We know that one, but I don't think we know the next one. Theta of 4 will give us inverse secant of 4/3. And we don't have a special value for that, so we'll just keep that where it is. But notice these are in the arc 0 to pi over 2. So both of these are contained in this part of the arc, 0 to pi over 2. So this is where the inverse secant is positive. So if we have some absolute values here, this will tell us how to interpret. So in this case, inverse secant, in this, let me just say, let me write it this way. Let's see, in this particular case, here we go. So I'll just say, let me write it this way. This, we know where inverse secant is. This determines the absolute value computation. I'm just going to write it now because I haven't done it yet. This determines the absolute value computation. So let's do it. Let's think about that first. I can't really say definitively what it is. We know what the inverse secant is. That's not going to help us. So what we want to know here is that when we've got 1 and greater, the output of the inverse secant lives here. And so whatever trig function we get, we'll have to compare it to that. And then we'll say, oh, for this trig function, it's negative. Oh, for this trig function, it's positive. So this will determine the absolute value computation. So that's why it's very important to think about what you're doing when anytime you get inverse secant. It's just not as user friendly, but we'll live with it. So now when we look at this, we've got the x squared, we need the dx. Let's go ahead and do that. So dx will be what? 3 secant tangent. So that's just the derivative of secant. So let's take care of that. I want to do all the extra work here so you can easily see it. And now we want to use this. Let's figure out what the radical is going to be. So we have x squared minus 9. So this is going to be what? So we're going to have a 9 that we can factor, and we'll have the secant squared theta minus 1, our old friend, Pythagorean identity. So of course we get the square root of 9, which is the square root of 9, which is 3, which is the square root of 9, right? Okay, and then of course times the square root. This just gives us the tangent squared from the Pythagorean identity. So again, you can shortcut this, but I want to work it out in detail the first time. So this will be the absolute value of tangent theta. And like I said here, this determines the absolute value computation. For these values of theta, the tangent is positive or non-negative. So this, like I say, this determines the absolute value computation. So we've got it. So if you want, just kind of put a little red box around this because it's actually quite important. If we have to introduce a negative sign, that will change the answer, but we don't in this case. So this will be 3 tangent theta. All right, so now we're good to go. So boom, let's put a box around that. So what does our original integral look like? So let's go ahead and write it down. So now we have equals. So we have a lower limit of inverse secant, and we'll draw a triangle for that, because it'll help us when we need to evaluate, and an upper limit of pi over 3. So here, if you think about this particular triangle, let's see. So here we have theta. So in this case, let's just do a little sidebar here. Secant theta, for this case, for the 4 case, is 4 over 3. So if we have the theta here, we have the hypotenuse adjacent, and so that'll be a 16 minus a 9, which is a 7. So that gives us a square root 7. So this triangle here can be useful to us. So this basically just takes this computation and converts it to a right triangle. So again, the right triangles are so useful. These ratios of sides of right triangles are extremely useful, and that's why we're grateful to the geometric interpretation of trig, because it helps us to solve these problems. Otherwise, we would really struggle. So we're grateful to that interpretation. So now we've got this, and now we can substitute everything. X squared would just be 9 secant squared. So 9 secant squared. And then downstairs, notice we have the square root. That's going to be what? 3 tangent. So the square root is 3 tangent. And then dx is right here. 3 secant theta, tangent theta, d theta. So when you think about this particular integral, you're thinking, oh, here we go, Professor Ron. I'm glad you did the secant cubed integral. We don't have to do the reduction formula because we proved it using integration by parts. Notice the 3's absorb, the tangents absorb, and we're left with the integral 9, which we can factor, secant squared times secant, secant cubed. So that's why I was talking about this integral before. It's a very important integral. And of course, put the -1 there. No need to leave that out. So at this point, we've reduced this to one of our favorite integrals. Well, I don't know if it's our favorite integral, but at the time I told you we're going to need to use it again. And here's the case. So the idea here is now use formula for this integral. We don't want to start over. I mean, that's too much work to do that over. And of course, you could use the reduction formula, but you already know the formula. This should be on your note card. So we've already done the sweat for this one. So we're going to use it. So now remember, it's the 1/2. So this equals 9. We have the times the 1/2. And remember, we have the secant theta, tangent theta, plus the natural log. Remember, we had the integral of secant, plus the natural log secant theta plus tangent theta. And evaluate secant inverse 4/3 and pi over 3. So when you think about this particular problem and you consider where we've come, we have this original integral which fits the secant trig substitution here. We have our right triangle. We need to change the limits. We get one limit that we know from the unit circle, and the other limit is not as nice, but we can configure it with a right triangle. Again, just take this as secant theta equals 4/3 for the lower limit of 4, which gives us this special triangle, which will allow us to navigate this procedure a little bit better. Okay, so now let's use the fundamental theorem. So again, this is the integral we derived last week with integration by parts. Remember, I'd said, okay, this is an integral we're going to see again. Well, that's an important one. So you don't have to rework it every time. You should have that as a reference on a note card or something, and I want you to use it. So now we have 9/2. So we'll substitute pi over 3. So we have secant pi over 3 times tangent. And if you want, you can go ahead and put those in parentheses, pi over 3 plus natural log secant pi over 3 plus tangent pi over 3. So that's the first part. And then minus, and I'll go to the next page, but I'll just go ahead and fit this right here so it's not all pushed over there. We'll run out of room. So now we do it again. That is, we have the 9/2 here, so we're doing the lower limit. So we have secant. Well, here's where we can flex our trig muscles a little bit. We have, in this particular case, secant of the inverse secant. So that absorbs. That'll just give us a 4/3. I'll write it out, but this will be secant of the inverse secant of 4/3. So that'll be a nice absorption. And then, of course, we're going to have tangent. We'll get to use this triangle because this is really the theta here. So this will be tangent of inverse secant of 4/3. So we can use the triangle because this corresponds to the theta there. And then plus natural log. Again, we'll have secant of, in this case, inverse secant, same thing again. I want to write this out so you see exactly what I'm doing. And then, of course, we have the same thing here, plus tangent of inverse secant. So that's the only thing that's a little bit complicated. Once you draw your triangle, you can now use your triangle. So again, just in this case here, just remember the theta for this is, as we've got right here, inverse secant of 4/3. So that's what we're using to do this computation. So now we can finish it up. So we get 9/2. So now we've got secant of pi over 3. That's just basically the cosine of pi over 3 reciprocated. So that'll be a 2. So we have 2. And then, of course, tangent of pi over 3, our old friend, root 3 over 2 divided by 1/2, root 3. Plus, we'll keep this all in parentheses. And now we have natural log. And we'll just repeat these, 2 plus root 3. And now here we can use our triangle. So of course, these absorb, these are inverses. So we just get 4/3. And then we have tangent of theta. So now, of course, tangent will be opposite over adjacent. So this will be square root 7 over 3. Just go to our triangle, opposite over adjacent. And then we have plus natural log. And these are nice positive numbers, fortunately. So we've got what? 4/3. And then we have plus, in this case, like we had before, square root of 7 over 3. Now, when you look at this and you're thinking, you know, Professor Ron's going to use the differences of the logarithms. So let's go ahead and see what we can get out of this. Now, notice when we multiply this out, we're going to be able to combine some things. So let's just go ahead and do that. Here, the 2's absorb. So we have 9 times the square root of 3. And then in this particular case, we have plus 9/2 is going to multiply everything. 9/2 times natural log of 2 plus square root 3. And here we have minus. So we have minus 9/2 times 4 root 7. 3 times 3, 9. And then we have a 9/2 with a minus, minus 9/2 natural log And I can go ahead and that's a common denominator, 4 plus root 7 over 3. So now we're looking at this and saying, okay, this isn't half bad because now notice we got the same coefficient, so we can combine these with the logarithm identities, the quotient rule. And then of course, these two, these absorb. And of course, notice here, the 2 absorbs into the 4. So this gives us 9 root 3 minus the 9's absorb, and 2 into 4 is 2. So we get minus 2 root 7. That's a really nice computation, isn't it? And so here we can just do the quotient because we have the minus. So we have minus 9 over 2 natural log. So we have 2 plus root 3. And then, of course, when we divide by this, the 3 will come upstairs. So this will be 4 plus root 7 divided by 3. So that'll just round about upstairs, reciprocate, and multiply. So this gives us 9 root 3 minus 2 root 7 minus 9 halves natural log. And then, of course, if you want to multiply through, you can. That'll give us a 6 plus a 3 root 3 and 4 plus root 7. So when you think about these particular problems, and notice here, when I've got the plus here, that's the plus, so the minus, so that retains the plus here. That retains the plus. So remember, I keep using base A logarithm of x minus base A logarithm of y equals the base A logarithm of x over y. And that's what I've used here. And of course, we retain the positive, so I need the plus there. So now what we're seeing with these techniques, when we work trig sub, just like when we do partial fraction, we break down the fraction using the fact if we've got a linear factor or an irreducible quadratic. With the trig sub, we simply notice what type of Pythagorean radical we have. If we have the square root of u squared plus a squared, we use the tangent substitution. If we have the square root of a squared minus u squared, we use the sine substitution. And if we have the square root of u squared minus a squared, which we have here, we use the secant substitution. Now, if we do a definite integral, ladies and gentlemen, the additional work is simply to change the limits. You don't want to work the problem through indefinite and then go back to the original variable and substitute. That's just too much work. I mean, that doesn't even really make sense, actually. But it's not a bad way to do just as an academic exercise. But in practice we'd never do it. So the idea is that when you're looking at this, you're thinking, okay, well, let me just go ahead and change the limits and convert everything to theta, and then you have this nice way of working with the triangle, which mimics what we have here. Now, of course, this takes a little bit more arithmetic, but it hinges on the fact that we already had the antiderivative of secant cubed. So that's a standard integral formula that you want in your back pocket. You don't want to have to rederive that. That's too much. I mean, of course, and if you forgot it or didn't have it down, you could use your reduction formula. But this is such a nice, neat formulation of it that we got through integration by parts, and it's fairly easy to use. We can see the substitution process was not use our unit circle, and then of course our wonderful logarithm identities that we have to get a really nice solution. Okay, so that's a very clean real number, so to speak. It's nice and tidy, so to speak. Now the idea is with the trig substitution, and I want to share this with you. It's really how I usually try to start out with the trig sub. But what I wanted to do was to work with this, with the three cases first, and then go back to some of the, what they call special formulas. Now, and I want to share these with you. These are the special formulas that are in your textbook. It's called Theorem 8.2. Now, what I wanted to do is just share these with, mention that again, when you find these in a theorem or you find these in an integral table, the trick here was to use the trig sub. So you can actually look in my lecture notes on Blackboard where I've derived all of these, and the derivations are fine and nothing wrong with that, but it's just basically what we've done in the problems. So what I want to focus on right now is the fact that if we have a radical like this with nothing else, okay, so we just start with the Pythagorean radical, the one that uses the sine substitution, the one that uses the secant substitution, and the one that uses the tangent substitution, as I've notated here. With the trig sub technique, we can derive all of these formulas, just like we were doing in our examples. And the idea is that you notice the form of these. It must have been the case that we pushed forth the secant cubed integral. And if you look in the notes, you'll see that. So these are what we call special integration formulas. Dr. Larson puts this in your ebook. And so if you want to go ahead and work through these derivations, be my guest. They're fun to do, but I will not test you on it, but I will want us to be able to use them. And I want to show you an example of where we actually do. So when we have the square root, or the integral of the square root of a squared minus u squared du, we get this antiderivative, 1/2 times the quantity u times the radical plus a squared times the inverse sine of u over a plus a constant. Now, that's a fairly busy formula. So, and it's done in the abstract, and that's fine. But the first time through, it's a little bit difficult to do completely in the abstract. And I'll say more about this in a minute. And then, of course, with the secant substitution that we have here, we get, again, a formula that looks like the antiderivative for the secant cube that we just did. And then for the tangent, that is tangent substitution, we get likewise a very similar formula. You see, these are very close. They only vary in very small ways. So the idea here is that we don't want to have to start from scratch. When you take Calculus 3, these integrals will come up, especially with arc length and also with surface area that you see here. And I'll say, all right, kids, let's just take out our Calculus 2 special integral formulas and make quick do of these particular problems. So what I want to do is take advantage of one of these. So I've got an example right here. So notice, here's an example. For instance, say we have y equals x squared. That's just your standard curve quadratic. And we let x live between 0 and 1. Now you're thinking, that's a nice college algebra function, but we didn't compute its arc length. So here's what I want us to do. Compute length of curve for this interval. And this is where these special formulas are very useful, and you can see why we didn't do it at the time. So now we can say y prime equals 2x. So this implies, using our radicand for the arc length formula, 1 plus y prime squared will now be 1 plus 2x squared, which is 1 plus 4x squared. So this implies that our element of arc length, ds, will now be the square root, and we'll do it so it looks like this. We'll just use this one. This will be 2x quantity squared plus 1 squared dx. So now you're seeing that this is going to match up with this special formula. And so we'll be able to use it. Now, let's go ahead and write down the formula. So this implies from our techniques in chapter 7 that the arc length will now be the integral 0 to 1 of the square root of 2x squared. So this is easy. This is not like the difficult trig subs with all those, inverse trig functions that we had to deal with. This is a lot easier. So now we look at this and we say, okay, this arc length requires this special integral formula. And we've got u is 2x, u equals 2x, a equals 1. How nice, 1. So du equals 2 dx. So we just need to make an adjustment. So this will equal, in this case, 1/2 the integral 0 to 1 square root 2x quantity squared. So this is like we're doing calculus 1. I wanted to save this for last when it would be easier for you, 2 dx. So now this is just basically what we do when we use an integral table. So this is table ready. That is, note here, this is ready to go. We have, in this case, u is 2x, a is 1. We've got the du, so this can be completely transformed into the u integral, just like we did with the trig integrals. So let's get our new limits. So u of 1 will be 2 times 1, or 2, and u of 0 will just be 0. So now we'll transform this. So this will be 1/2 0 to 1, excuse me, 0 to 2, ding, 2, square root u squared plus, and of course now we have a 1, so we need to leave that as 1, du. So this is exactly this. That is, u is taken care of, and a is just 1. So now we just fill this in. So we've got the 1/2, which is on the outside. Now we have another 1/2, and we have u square root u squared plus a squared, in this case, plus 1, plus, now we got a 1, so that's just 1, natural log u plus square root u squared plus 1 0 to 2. So now we're like, how nice. But only because we have the special integral formulas based upon trig sub. So now we've got what, 1/2 on the outsides. Let's go ahead and substitute. So we put in 2. So we have 1/2. So we have 2. So 4 plus 1, square root of 5, plus natural log. So we'll have a 2 plus, again, square root of 5. And now we do the minus. But now, of course, we have the 0. So this is just the 0, 0 times the square root of 1. That's just 0. Plus natural log of 0 plus square root of 1. So that's not going to give us anything, but that's okay. We need to write it down. So now we can go ahead and multiply all this out. All this is 0. This part just equals 0. Log of 1 is 0, 0. That's all 0. So we get 1/4 times 1/2 times 1/2 is 1/4, 2 root 5 plus natural log 2 plus root 5. Now, what we're seeing here is that this was not a trivial exercise, because we could have not even attempted to do this with the techniques we already knew. So now what we're seeing is with our special integral formulas, we have now a nice way to compute integrals, which will often come up with arc length and surface area calculations. So what we're seeing is that what would have appeared to be a very simple arc length calculation was just this Pythagorean radical integral. Again, this substitution is all Cal 1. We made it table ready, and then we just substitute using the formula. And now we see that this really wasn't very trivial, that we get 1/4 times the quantity, 2 times the square root of 5, plus the natural log of 2, plus the square root of 5, which is really not something that would have just rolled off the tongue. So this is why I mentioned this early on. I said, we're going to avoid some of the college algebra functions that we love that are near and dear to us because we don't have the techniques to actually compute the antiderivatives. And now you can see that this is really very straightforward. The algebra is minimal. Before, we had lots of algebra to do to clean up the expression to keep our fingers crossed that we'd get a perfect square. Here we don't have the perfect square, but we have the special integral formulas with the trig sub development to get a nice, neat answer. So I think now you can see that we developed some really good techniques that are going to cover a lot of antiderivatives that you're going to encounter. And then, of course, as I've said before, as you take more engineering, more STEM courses, you will learn other techniques that will be germane to the types of problems that you're solving in the class. If you're ever interested, you should check out the Schaum's outline on advanced calculus. It has a nice section on elliptic integrals and Fourier analysis, which I think a lot of you would be interested in. Like I say, there are many jobs open to electrical engineers. When you think about the grid in Texas and the maintenance of that, that would be a wonderful STEM job. I think in another life, I may have still had the musical part of me, but I might have been someone who worked with oscilloscopes at a electrical engineering firm. It's fascinating. One of my favorite classes in grad school was partial differential equations, and this was taught from a professor at Texas A&M who was originally from Russia, and his field was PDEs and actually complex analysis. So he merged the two, and very interesting subject matter. So what we'll do on Wednesday, ladies and gentlemen, again, I may say maybe just a couple more things about this. I think I've covered pretty much everything I want to do. We'll focus on some review problems for the test and just kind of go back to the types of examples that we've done. If you want to go ahead and look at the practice test, that will give you a good indication of the types of problems. And also remember, we won't have formal proofs on the test. It does help you to understand what I've done, but I won't test you on formal proofs. And of course, if I come up with a way to do that, I'll let you know. But the problems will be very much oriented in the same vein as you saw on the first test. So enjoy the nice weather. It's going to get a little bit cooler this week, but not cool like we've known. Just, I guess, our basic Texas weather that we all know and love. But I appreciate your attendance today. Stay well, be safe as you go out. And of course, I'll have 2 sessions today. I'll send out email invitations. So if I see you there, fine. If not, I'll look forward to seeing you at our next class. Everybody have a good day.